So let us suppose that we have a transform t, and that t goes from boop, boop, boop. Let me draw in my bold R's first of all. Whoop, 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 whoop. And let's say that t goes from n to m. And let's assume, and this is crucial, that t is a linear transform. And let's see if we can prove the following. That if I give you a linearly dependent set, so let's say the set of vectors v1, v2, and v3 is linearly dependent, this implies that the set of transforms of those vectors, t of v1, t of v2, and t of v3, is itself linearly dependent. And we want to prove this. Well, first of all, remember that what linearly dependent means is that one of the vectors can be written as a linear combination of the other two. So for example, perhaps v3, or actually it would be any of them actually. So without loss of generality, we'll say v3. v3 would be some constant times v1 plus some constant times v2. That's what it means for them to be linearly dependent. Well, what we can do with this, let's look at this right here, is let's solve it for v3. So let's say 0 equals c1 v1. I'm sorry, was solved for v3. Let's move everything over to one side. Plus c2 v2 minus v3. Now in this case, I don't want to assume that the coefficient I need on v3 is -1, but I just want you to show that the other way of putting this is that there is a way to write this so that these would all add up to 0. So what I'll do is I won't assume that this is minus v3. I'll just say it's some coefficient times v3. And now here's how my proof's going to go. First of all, I'm going to say that I know that the 0 vector is equal to t of the 0 vector. Why? Well, because t was linear. And one thing that follows from a linear transform is that if you plug 0 into it, you still get 0. Well now, what else is 0 equal to? 0 is equal to a sum of these vectors right here. And I haven't been writing the little arrows over the top. I will now do that. So this is a transform of c1 v1 plus c2 v2 plus c3 v3. I'm going to be very clear that all I did is I said that 0 equals the transform of 0, which I can do because it's linear. And I've also done that, well, what is 0? 0 is something times v1 plus something times v2 plus something times v3. So all I'm doing is I'm just plugging in synonyms. It's like you said cat, and I went, oh, animal. Now, granted, in that case, those aren't perfect synonyms, but you get the idea. All I'm doing is swapping in symbols. Well, now, if t is linear, that means that if I'm doing a transform of a sum, I can just do the sum of the transforms. In other words, I can rewrite this as the transform of this first vector, c1v, plus a transform on the second, c2v, plus a transform on the third, c3v3. Okay? Well, we're almost there. Remember, I want to show that t of v1, t of v2, and t of v3 is linearly dependent. I don't care about t of c1 v1. But that's okay, because since this is a linear transform, I can also pull out constant scalars. Now, keep in mind, these constants, these coefficients right here, are not vectors. They're scalars. They're just regular old numbers. And so they can come outside. So I can rewrite this as c1 t of v1 plus c2 t of v2 plus c3 t of v3. And now look at what this means. Can I take some constant times t of v1 plus some constant times t of v2 plus some constant times t of v3 and get that to add up to 0? Well, I sure can, because it says right here 0 equals this, which equals this, which equals this, which equals that right there. And if I wanted to, I could actually solve for one of them. Let's say I solve for t of v3 again. So I would have negative c3 t of v3 equals c1 t of v1 plus c2 t of v2. And then I could divide through by negative c3, and I would have t of v3 by itself. So the point is, both interpretations are enough for me to say this is linearly dependent. I can stop right here above the squiggle, because these can be written to add up to 0 with some constant coefficients. But if I really, really am just like married to that notion of, well, actually, I think of linear dependence as I can write one of these vectors as a sum of the others. Okay, cool. I can still do that. If I have this equals 0, just move one guy over, divide off the coefficient, and this guy is a constant, is a linear combination of these two guys. So either way, however I'm thinking of it, I have that, therefore, v1, v2, v3 being linearly dependent implies that the set t of v1, t of v2, and t of v3 is also linearly dependent, which was what we wanted to prove. And there we go.